Okay, so those examples I used were simple relationships, normally one-on-one. Time versus disease development, relative humidity versus spore germination, or whatever the case may be. I just want to quickly mention multiple regression, and you get other related models. Very often when we do a field trial, we'll have temperature, rainfall, relative humidity, whatever the case may be. We'll have more than one variable. And there are various multiple regression models that can study the relationship between several independent or predictive variables. Okay. They can determine the number of factors or dimension and their contribution to the relationship. So we have some programs that will do a multiple regression model, and it will throw out those variables that are not significant. We call it the stepwise or step down or step up regression analysis. Okay. Now, normally a multiple regression, most of the correlation will assume linearity between dependent and independent variables. So it has its limitations. And if you think back of the graph I had between relative humidity and spore germination, which is nonlinear, it's already going to have a limitation if you include that as a variable. But there are ways of linearizing okay, relationships using a log transformation. So very often, instead of, like in the case of the relative humidity one there, you might use log relative humidity to get a linear relationship. Okay, so there are ways of getting around that as well. Here's an example where you have yield loss due to disease, and you measure disease every week. Okay, and you're assuming that there isn't a single critical point, but that the effect on yield is going to be incremental, in other words, depending on how much disease there was at each growth stage. So you might measure disease for 6 weeks, and you'll put that in a multiple regression model. Okay, and you also get an analysis of variance out of that, and it will tell you that your model is significant, only just. Okay, right, 5%. It will give you an R-square value, which basically would be 83%. Okay, and that tells you that 83% of the variation is accounted for. It gives you standard error, but this is the important one here. It gives you a model of yield loss. Yield loss is equal to basically a residual value, an intercept value there, time plus 1.56 the amount of disease you had at week 1, minus 1.578 week 2, and eventually at week 6, 0.93 times week 6. So you'd put that into a spreadsheet or something like that, using those parameters, and it will tell you how much disease you can expect, okay, based on the amount of disease at those various weeks. So that's just an example of applying a multiple regression analysis. It works on exactly the same basis as a linear. It's just a whole lot of linear models added together. It's probably the simple way of thinking about it. Then I did mention that we have stepwise regressions. We have forward selection, backwards elimination, and what you can do is, instead of using the full multiple regression analysis, you can use a stepwise analysis. And what that will do is we'll go through your variables, and it will throw out those variables that are not contributing significantly to the model. Okay, so here's a backward elimination. It just means it's going to work backwards. It starts from their whole model and then throws out what it thinks is junk. And you could end up with a yield loss model that only includes disease at week 2 and week 5. Right? Those are the critical evaluation. So it means next time around, I don't measure disease at every week for 6 weeks. I measure at week 2 and I measure at week 5. And I've got a fairly good model. Okay. And the question is, why time and money measuring weekly when 2 and 5 weeks will suffice? So that is then where something like a stepwise multiple regression becomes useful. Okay. And they're all basically these linear models added together, and if they're not significant, they get subtracted again. It's the basic principle of what's happening. You can also get multiple non-linear models. We're developing a model now for fusarium colonization of maize. And here's the relationship with humidity and temperature. And you can see that they are non-linear models. And you can see then you have almost, well, you call it a multiple non-linear model instead of a multiple regression, which is linear. Okay, so you can have these multiple models that can also account for non-linear relationships. Okay.